Differential Equations, Part 1, Basic DE Theory. What is a differential equation? A differential equation is any equation containing one or more derivatives. Examples include the first derivative of y is equal to 3x plus 4. The second derivative of y is equal to the cosine of x plus the natural log of x plus 1. The first derivative of y is equal to 5 times y. The first derivative of y is equal to negative 1 times y squared. The second derivative of y is equal to 5 times y plus 7 times the first derivative of y plus 9. In each case, we have an equation containing one or more derivatives. Terminology. DE stands for differential equation. IVP stands for initial value problem. In an initial value problem, the solver is given information that will allow them to find the value of constants in the general solution. Many differential equations fall into special cases for which a general solution exists. We will present several common DEs and their general solutions that students are likely to encounter in single variable calculus. For students new to calculus, it is frequently helpful to memorize these general solutions until they have acquired sufficient knowledge and experience to derive the solutions on their own. Case 1. The growth rate is constant. The differential equation in this case is the first derivative of y is equal to a constant. The general solution for this is y equals that constant times x plus a constant. Let us consider an example. A balloon rose with an initial velocity of 12 meters per second and constant acceleration of negative 9.8 meters per second squared. In this case, we are told that we have constant acceleration. Therefore, our DE will involve acceleration. It is important to note that acceleration is the rate of change of the velocity. Therefore, A is equal to V prime. Starting with our DE, we have that the acceleration is equal to negative 9.8. Since we've noted that A is V prime of t is equal to negative 9.8. In addition, we know that V of 0 is equal to 12 since the initial velocity is 12. Taking our general solution, V of t is equal to negative 9.8 times t plus c. Applying the initial condition that V of 0 is equal to 12, we have V of 0 is equal to negative 9.8 times 0 plus a constant. Since V of 0 is 12, 12 is equal to 0 plus a constant, and therefore the constant is 12. And the general solution to this differential equation is V of t equals negative 9.8t plus 12. Case 2. The growth rate of y is proportional to the time. The differential equation in this case is y prime equals a constant times t, where t is a constant of variation. The general solution for this differential equation is y equals 1/2 k t squared plus a constant. An example. The instantaneous velocity of the rocket was proportional to the time since leaving sea level. After 2 hours, the velocity was 200 kph. In this case, our differential equation is V of t equals kt. We are given some conditions to allow us to find k. We're told that the velocity after 2 hours was 200 kilometers per hour, and that the position at time 0 was 0, since we are told that it is time since leaving sea level. Sea level is a height of 0. Taking our differential equation, V of t equals kt, we plug in the fact that V of 2 is equal to k times 2. Since V of 2 is 200, 200 is equal to 2k, and k is equal to 100. Plugging this into our general solution for our differential equation, we have x of t is equal to 1/2 kt squared plus c, or better yet, 50 t squared plus a constant. Plugging in the fact that x of 0 is equal to 0, we have x of 0 is equal to 50 times 0 squared plus a constant. 0 is equal to 0 plus c, and therefore the constant is 0. Therefore, the general equation for this differential equation is x of t equals 50t squared. We will consider the other cases in the videos that follow this one.